Hello, AP Chemistry students. It's me, Dr. V, and it's a good day to review for the AP Chemistry exam. Isn't every day a good day to review for the AP Chemistry exam? You knew I would say that. In this webcast, we're working through free response question number 6 from the 2023 exam. This is one of the short free response questions, and that means it's scored out of 4 points. Could have 2, 3, or 4 parts. We'll find out. Get your calculator, your periodic table, and your formula sheets, and keep them handy. What I want you to do is use this webcast as an opportunity to improve your response writing skills. Let me introduce each part of the problem, pause the webcast, try to answer it on your own, and then listen to my explanation. We really want to make this very active on your part. That'll make it possible for you to score your own work on each part as you go. Did you earn the point? Did you not earn the point? What did you do well in your response? What do you need to enhance in your response? Was there something you forgot? Was there a mistake that you made? Putting all those pieces together. That's really important. Let's jump right into the problem. Answer the following questions related to HBr liquid and HF liquid. In the following table, Part A, lists all of the types of intermolecular forces present in pure samples of HBr liquid and HF liquid. Notice we said all of the intermolecular forces, so we have to start right at the beginning. We know all matter can participate in London forces, so we're going to put that down for both of them in the table as we fill it out. Now, the other thing to note is that HBr and HF are both polar molecules, and because they're both polar molecules, they can both do dipole-dipole attractions. But there's something HF can do that HBr cannot. HF can do hydrogen bonding. Because it meets the definition, it's got a hydrogen bonded to a nitrogen, oxygen, or fluorine, and then that hydrogen could be attracted to another molecule's nitrogen, oxygen, or fluorine. So HF can do hydrogen bonding, HBr cannot. And these are the things you needed to have listed in the table in order to earn 1 point. The enthalpy of vaporization for each liquid is provided in the following table. So we've got the 2 numbers here. Based on the types and relative strengths of intermolecular forces, explain why the heat of vaporization of HF is greater than that of HBr. Well, we know what kinds of intermolecular attractions are in each one. We just wrote that down in Part A. But looking at the numbers, HF having a higher enthalpy of vaporization means it takes more energy to vaporize HF molecules. Whichever species in the data table that you're given has the higher enthalpy of vaporization, it must have stronger intermolecular forces. And that's really the key point we want to make here. The combined strength of the hydrogen bonding dipole-dipole attractions and London forces that exist between molecules of HF is stronger than the combined dipole-dipole attractions and London forces of HBr. How do we know that? Because HF has the higher enthalpy of vaporization. Therefore, more energy is needed to overcome the IMFs between HF molecules than between HBr molecules. And that's really the gist of our answer and what we needed to say to earn 1 point. You did need to make sure you were comparing both species and specifying the intermolecular attractions that we had already talked about in Part A. There's a second part to Part B. Calculate the amount of thermal energy in kilojoules required to vaporize 6.85 grams of HF. We want kilojoules, we have grams, we need a mass-energy relationship. Well, we have one. We know for HF it takes 25.2 kilojoules to vaporize 1 mole of HF. But we have grams of HF, so we're going to need to convert our grams of HF to moles of HF, which means we need the molar mass of HF. You look on your periodic table, it's easy to calculate the molar mass of HF is 20.01 grams per mole. You don't really have to show work for calculating the molar mass, but you do need to use a correct molar mass in your setup. So I'm going to take my grams of HF, convert it to moles of HF, and then I'm going to use the heat of vaporization, which is a kilojoules to mole relationship, to get my final answer. So I can convert to moles of HF, like I said I was going to, and then I'm going to multiply by the heat of vaporization of HF, and I get an answer of 8.63 kilojoules. I had to put in 8.63 kilojoules to vaporize the 6.85 grams of HF. Now this was also worth 1 point. You have to have a complete setup and the correct answer. Based on the arrangement of electrons in the bromine and fluorine atoms, explain why the bond length in an HBr molecule is greater than that in an HF molecule. We're told this. HBr has a longer bond length than HF. What we really need to do is think about atomic structure. It's not what they said. They didn't say, and principles of atomic structure. But that's really what we mean here. So for fluorine, there are 2 occupied energy levels. Energy level 1 and energy level 2. For bromine atoms, there are 4 occupied energy levels: energy level 1, energy level 2, energy level 3, and energy level 4. We see this in the periodic table. Fluorine's in period 2, bromine's in period 4. That tells us the highest occupied energy level. So how do I explain it? Well, the valence electrons in bromine, which are at energy level 4, are inherently farther from the nucleus than the valence electrons of fluorine that are in energy level 2. As we add additional energy levels, they get farther away from the nucleus. And I needed to state that explicitly. Therefore, the bond length in HBr is longer than the bond length in HF. You did not have to draw the Bohr models. You did not have to write out electron configurations. I chose to do that here just to help you visualize that. And all that was worth 1 point. How did you do? Right? So this was a question that started with some thermochemistry and then switched to atomic structure. All very doable. The average score, however, on this question was 1.95 points out of 4. So most students earned 2 points on this question and not all 4. You have to be careful when you're discussing things in atomic structure, number of energy levels, really make sure you do that, grams to moles, moles to grams, those kinds of conversions, making sure you have the right kinds of intermolecular attractions. There was a lot going on in this question, even though it's a short question. If you found this webcast to be helpful, like the video and leave a comment, and remember to subscribe to my channel so you get all my latest updates. I've got a few more 2023 videos to make, exam review videos from past years. You can find it all at my YouTube channel. Have a great day and keep studying chemistry.